Okay, so our last topic in space exploration is topic 8, which is people in space. And so we'll just start by watching a couple of these videos here on the space race. So firstly, breaking free of Earth's gravity. So anything that escapes Earth's gravity has to completely, it has to reach a speed of at least 8 kilometers per second or 29,000 kilometers per hour. So Sputnik 1 and Vostok 1, as was mentioned in the video, Sputnik 1, the Soviet Union was the first to successfully orbit a satellite with no astronauts inside. Oh, just keep in mind, they called them cosmonauts. So they launched Sputnik 1 in 1957. The Soviets were also the first to put a person in space. On April 12, 1961, it was cosmonaut Yuri Gagarin in his Soyuz class space capsule Vostok 1, which orbited Earth once at an altitude of 302 kilometers for 108 minutes. So this is a picture showing that. Vostok 1 traveled at close to 29,000 kilometers per hour. It carried the cosmonaut Yuri Gagarin. He was the first person actually to see that Earth is round. So he re-entered the atmosphere and his capsule parachuted to the ground. And he ejected from his capsule before it landed, and then he parachuted to the ground separately. Alan Shepard and Freedom 7, Project Mercury. So the ultimate goal of Project Mercury was to place an astronaut in orbit. So May 5th, 1961, aboard the spacecraft Freedom 7 was Alan B. Shepard Jr. He became the first American astronaut in space. So Shepard flew a suborbital flight. Suborbital trajectory, it's one in which the spacecraft is boosted above the atmosphere and then it falls back to Earth without going into orbit. And then in 1962, astronaut John Glenn was the first American to make a full orbital flight. So the Apollo program next was designed to send a 3-person team to the moon, land 2 of them, and bring everyone back safely. So it consisted of an orbiter, which is the command and service modules, and a lander, which was the lunar module. So here the moon landing in the summer of 1969, Apollo 11 carried the first humans to the moon. Neil Armstrong was the first to step onto the moon's surface, and then after that was Edwin Aldrin. Michael Collins manned the command module in lunar orbit, so he stayed inside. As Neil Armstrong stepped onto the lunar surface, these were his famous words: "That's one small step for man, one giant leap for mankind." And then this was a picture taken. Neil Armstrong took this picture. Edwin Aldrin working on some equipment near the lunar module. Meeting in space. So Soviets and Americans worked together. So the Cold War tensions between the Soviets and Americans were easing in the 1970s. And the Americans proposed a joint mission of the two countries. They would use the existing hardware, the Apollo and Soyuz, in a linking mission. So the Apollo-Soyuz test project, it was flown in 1975. It was the first international space mission. Just a little bit of comparison between the Soviet system and the American system. Okay, so life support compatibility. So astronauts, like all people, need to continually breathe oxygen and generate carbon dioxide and water vapor. So the spacecraft, it needed devices to continuously replenish oxygen and to eliminate excess carbon dioxide. So the Soviet and American engineers They removed the carbon dioxide and the humidity by using the same chemical reactions, but they approached the problem of oxygen supply differently. So here we can see the two systems, the Soviet system and the American system for oxygen production in space. So if we look at cabin atmosphere, the Soviet system was 80% nitrogen, 20% oxygen at normal air pressure. American, 100% oxygen, about 1/3 air pressure. Advantages of the Soviet system, its simplicity, minimal danger from fire. American system, a switch from cabin to suit system. Oxygen would not subject the crew to decompression problems. Disadvantages for cosmonauts would be they would be exposed to potential decompression should they have to switch to a spacesuit life support system in an emergency. A disadvantage for the American system was from fire. Danger from fire, requirement for flame proofing all materials used in the cabin. The oxygen replenishment, for the Soviet system, they used chemical reactions with solid chemicals, and then the American system, they had oxygen stored in high pressure containers. Next, we'll look at the space shuttle. So the United States, they decided to develop a reusable spacecraft, the Space Shuttle. Up to this time, all spacecraft could be used only once. So a reusable spacecraft, it would lower the cost of working in the near space environment of a space station. So 56 meters long, a mass of 100 tons, the shuttle became NASA's primary launch vehicle. It is used as a lab to do experiments in space, to deploy satellites, to photograph Earth, to carry repair crews for orbiting equipment. So here we can see the image of that. When the shuttle lands in California, it's returned to Florida on the back of a Boeing 747. The shuttle is almost as big as the commuter jets that fly from Edmonton to Calgary. Columbia's first flight, the first shuttle, Columbia, flew its first mission to space in 1981. It's shaped like a plane because it glides to Earth with no power of its own. 7 months later, Columbia flew again. Canadian contribution, the Canadian-built space arm called the Canadarm was tested on this flight and has been part of all shuttles since. A little bit more about Canadian astronauts. In 1983, the Canadian Space Agency hired Canada's first team of 6 astronauts. Roberta Bondar, Mark Garneau, Steve McLean, Ken Money, Robert Tursk, and Bjarne Trygvason. In 1992, Chris Hadfield, Julie Payette, Mike McKay, David Williams, they joined the team of Canadian astronauts. I have a quick video here. All right, so continuing, next is the International Space Station. So it involves the contributions from 16 nations. So along with the United States, NASA, major partners in the ISS, the International Space Station, are Canada, the CSA, the European Space Agency, ESA, from Japan, NASTA, and Russia, RSA. So they provide an orbital laboratory for long-term research. There's research happening in biology, chemistry, physics, ecology, and medicine. All of those can be conducted. The science will cover all the sciences we do on Earth, but in that microgravity environment. Okay, microgravity meaning there is almost as much gravity in orbit as there is on Earth. So microgravity is used instead of zero gravity. So medical benefits of conducting science in space. It could lead to new drugs, a new understanding of the building blocks of life when we see how they behave in microgravity. Industrial benefits can lead to stronger, lighter metals, more powerful computer chips, understanding phenomena such as extreme temperatures and micrometeorites can help engineers improve spacecraft design. Observations of Earth will enable researchers to study changes to our environment, whether they're occurring naturally or by human action. Other benefits may also lead to advanced weather forecasting systems and the most accurate atomic clocks. Commercialization of space research will enable industries to explore new products and services. So the result of such innovation will create new jobs here on Earth as well as in space. The Canadarm, a little bit more about that. The Canadian Space Station Remote Manipulator System, SSRMS, or Canadarm2. It's a giant mechanical arm that's attached to the space station. So in 2001, Canadian astronaut Chris Hadfield traveled into space to help attach the Canadarm2 to the International Space Station. And then attached to the end of the arm is the Special Purpose Dexterous Manipulator, SPDM, which is also called the Canada Hand. There we go. There's the image of that. I'm going to pause here and we're going to watch this video on the International Space Station.